Hello, we're going to make 3 videos about ways to use Taylor series, Maclaurin series to help you solve problems in calculus. The first of these looks at evaluation of an integral by replacing the integrand with a series and then seeing what we need to do to the resulting series to approximate our value within a desired tolerance. So our start for most of these problems is going to be this table from page 620, which shows several important series. These are all ones you should know or know how to derive at some point. Now, you don't really have to memorize all of them. So there's a lot of related ones in here that if you know one, you should know the other. For example, the cosine series you see here can be done by differentiating the sine series. So we differentiate that series for the sine term by term. All these things, you'll find you get the cosine series. So knowing the sine series is enough to get the cosine series. Likewise, the second of the integrals here and the second from the bottom are very closely related. Of course, this top one is just the geometric series, but you might want to note that if you integrate 1 over 1 plus x dx, that you get the natural log of 1 plus x, and then modulo a constant. But nonetheless, it shows how these two series, the geometric series and logarithm, are related. So if you know the series up here for the geometric series, you should be able to get the logarithm series by integration. So you don't have to necessarily memorize all these things, but know how to go from one to the other. So we're going to employ, in fact, the logarithm series to approximate the value of the integral of log 1 plus t squared dt integrated from 0 to 1/2. We want to get this approximation with an error of less than 1/1000th. We'll see how series, in particular, surprisingly, the alternating series test will come into play to help us do this. Now, this example is from the book. It's page 617, example 4. This is worked out to some extent in the book. I'm going to go into a lot more details here and discuss more of some of the nuances and themes you want to be aware of when you try to do problems like this for other integrals. So our starting point is going to be to look at the integral, look at the integrand, log 1 plus t squared, and use the logarithm series, the log of 1 plus x, to try to get this. Okay. So if we look in our table on page 620, we have the series for the log of 1 plus x. We just looked at that one. So there it is. And we're going to think of series like this, or series formulas like this, as templates. And what I mean by that is that if we replace the x, anything we like, and do it consistently across both sides, we'll have another true identity. Second thing I want to keep note of here is this. Now notice we have written out here the first few terms of the series, and then we also are going to keep track of the kth term, the generic term. In this case, minus 1 to the k minus 1, x to the k over k. The nice thing about having this term is that if you have that term, you really have the summation formula also. Because now I can sum this as k runs from 1 to infinity, and actually just by taking this term and putting it behind the sum, I actually get the series for the logarithm itself in a summation form. So as I said, we're going to take this series for log 1 plus x, replace the x by t squared. So this is the template idea. If I replace x by t squared everywhere in this line, I can get another true formula. And so all I've done here is everywhere I see an x, I put in a t squared, and so forth. Okay, and this even works for the generic term. The x to the k becomes t squared to the k, and likewise in the sum, the x to the k becomes t squared to the k. Okay, now we're going to do a little bit of work with this. Here is that series from the last page. Our first step is just to work out the powers of t squared. So t squared squared becomes t to the 4th. T squared to the 4th becomes t to the 8th, etc. And again, importantly for the generic term, t squared to the k becomes t to the 2k. And then this also carries over to the sum. Now, let's take a moment to think about this power series for log of 1 plus t squared. It's not hard to show it converges for t's between -1 and 1. You can do that by the ratio test or just by realizing the original series for x converged for x's between -1 and 1. Convergence of the endpoints is always tricky, but we do get convergence at these endpoints. If you plug in t equals 1 and -1, you'll find you get a converging alternating series. In fact, you'll just get the alternating harmonic series. That happens at both ends, which is what the t squared helps do. Now, why do we want to check this? So this series converges for t's between -1 and 1. And in our problem, we're integrating for t runs from 0 to 1/2. It's important to notice that this interval is contained in the interval of convergence. Okay? If this interval, 0 to 1/2, had not been inside the convergence interval -1 to 1, then we could not have done this because the series would not be representing the integrand once t's got outside this interval of convergence. So I always want to check that we're working within the interval of convergence on problems like this. Okay, now that we have that, let's do the integration. So we now just put an integral sign outside our series relation from before. So here's the problem, integral 0 to 1/2 log 1 plus t squared dt. And since this is the series for log of 1 plus t squared, we can put the integral in front of that and the dt behind. Okay. Now we've just gone ahead and done this integration term by term. T squared integrates to t cubed over 3. T to the 4th becomes t to the 4th becomes t to the 5th over 5. And I don't want to forget that extra 2 down there. T to the 6th integrates to t to the 7th over 7. Don't forget that 3 that goes down there, etc. And for the generic term, we have -1 to the k minus 1, t to the 2k over k integrates to t to the 2k plus 1 over 2k plus 1, and then that other k factor stays down there. Now, a couple things to notice. Notice that I've left this denominator here as 5 times 2, and this one as 7 times 3, 9 times 4. I could have replaced these by numbers, 10, 21, 36. But when you work with series, it's probably a good idea not to be in too big a hurry to simplify things and multiply things out. When you do that, you lose patterns. So I'm going to leave these things in factored form like this, and that kind of goes along with the 2k plus 1 times k term here. And then you notice that we've introduced a 1 down here. The 1 is put in to kind of preserve the pattern with the 4, 3, 2, 1, you see, as the number behind the denominator that arises from the integration. So again, we're going to leave things unfactored so we can see patterns and make predictions. Don't, in general, multiply things out or be in such a hurry to do that. Now, our next step, we're just going to put in the limits of 0 and 1/2 and see what happens. So the limit of 0, if t is 0, of course, this whole thing becomes 0. And then when the only part that is non-zero is the t equals 1/2 portion. So we've just put in 1/2 for every t here. So for example, the t to the 7th term over here, when we put in t equals 1/2, becomes 1/2 to the 7th. And then in the step below that, we've actually just done these power multiplications. 1/2 to the 7th puts a 2 to the 7th down here in the denominator. So again, notice we haven't multiplied things out. Don't want to be in too big a hurry to do that. So the first term here becomes 1 over 1 times 3, and the 1/2 cubed generates the 2 cubed. The generic term works the same way here. We have the 2k plus 1 times k down here. There's that. And then the 1 over 2 to the 2k plus 1 brings in the 2 to the 2k plus 1 in that denominator, and this series keeps going. And as usual, this term is the term, we'd have to put in the summation sign. So actually we have here, this is an answer to the integral. That is the value of the integral from 0 to 1/2 of log 1 plus t squared dt. Of course, it's in a series form. It's kind of hard to see exactly how big or small that value is. So our next step is going to be to estimate the sum of this integral, of this series, and try to get a sum that estimates that answer to within 1/1000th, which was our tolerance. Now we're going to do that by the alternating series test. So let's first notice that if I look at the terms of this series, at least the absolute values of those terms, that's this one, then this, etc. Here they are down here. Notice they get smaller as we go out. The terms are decreasing. So as you move from one term to the next, notice everything in the denominator gets bigger, and bigger denominators make smaller fractions. So these terms, the sequence of terms is decreasing. Likewise, the terms go to 0. So if I let k go to infinity, the things I'm adding up or subtracting, which are these things, are getting small. They're going to 0. Now that means that the series, our answer, converges by the alternating series test. And so our idea is this. We know that this series is equal to a sum. There's the sum. We're going to approximate this sum, the answer to the integral. We know that this integral is equal to this sum. The value of this integral is equal to the value of the sum. So we're going to approximate the value of the integral or the sum by taking a partial sum. That is, by just adding up some terms of this series, but not all of them, but enough to get us within 1/1000th of the true answer. So over here in the next slide, we're going to go back to page 528. So we've shown this series converges by the alternating series test. If we look back at that test, we can approximate the series then by a partial sum. And in doing the alternating series test, back on page 588, we learned that the partial sum of the series that converges by the alternating series test differs in absolute value from the true sum of the series by, at most, there should be a less than the first term not used in the partial sum. So in our case, this says the following. So if we have the integral, which we know the answer is equal to this sum, we can approximate the sum by taking some finite number of terms. We'll call it n for now. And the term the error is bounded by the first term unused. So if the last term I used is n, the first unused term happens when k is n plus 1. The last used term was n. The first unused term is n plus 1. So I take this term of the series, I put in n plus 1 for k, and we get that, which simplifies to this form there. Now remember, we want this error to be less than 1/1000th. So we're going to figure out how big n has to be to make this thing less than 1/1000th. We can do that by trial and error. Okay. So all I have to do is find a value of n that makes this last expression less than 1/1000th, and this is easy to do with a calculator or with just pencil and paper. So we're just going to run through the values of n. Let's try n equals 1. This would mean we're using one term of the series and that the error is no bigger than the second term. So that'll occur when n equals 1, because this is the n plus 1 term. So if n equals 1, we get the second term, the 2 term. And we put in n equals 1 to this error term, we get 0.003 essentially, which is bigger than 1/1000th. That's too big. We want the error to be less than 1/1000th, so n equals 1 isn't going to do it. What about n equals 2? That means we use 2 terms of the series, and the error is no bigger than the third term. So here is the n plus first term here. If n equals 2, that'll give us the third term, and that calculation comes out to 0.00037, which is less than 1/1000th. So yes, 2 terms is enough. If we just approximate that sum of the series, by the first 2 terms, we're within 1/1000th. So we conclude by this, the integral we're trying to find here, we're going to approximate by just taking the first 2 terms of the series that we used, that we obtained in evaluating the integral. And those first 2 terms are when k equals 1, we get 1/24th. When k equals 2, minus 1/320. And that gives us a 37/960, or about 0.3854. So, and this calculation is within 1/1000th of the true value of the integral, because we know the error is no bigger than the next term of the series, which we verified up here was less than 1/1000th. So there's a lot involved in doing this problem. We had to pick the right series on page 320, make a substitution in it, check that the interval of convergence of the series does contain the interval of integration, and then do the integration of the series, and then decide, once we obtain that series, how we could take a partial sum to estimate its error. So a lot of stuff we've learned in the course comes together. So there are a few, though, important things to kind of rehash here. One of the things we did to start with was this idea of substituting in a given Maclaurin series. So we had the Maclaurin series of 1 plus x. We took that one off of page 620. It was very easy then to get the series for 1 plus log of 1 plus t squared by replacing x by t squared. This substitution is one of the most powerful techniques for generating new series from old ones. We had to be careful of the interval of convergence. So once we got the series for log 1 plus t squared, we saw that it converged for t's between -1 and 1. And since our integral went from 0 to 1/2, and that was inside the interval of convergence, we knew that we could use the series in working out the integral. Again, if this interval of convergence had gone outside of this interval of convergence, so if the integration interval had gone outside the interval of convergence, we could not have used the series to do the integral. And then finally, once we had the infinite series whose sum was equal to the value of the integral, we had to decide how many terms of the series we needed to take to get within 1/1000th of the true integral. So we had to work with the error in using the partial sum of the series. Now, this error estimate will often depend on what kind of series you have. We got lucky here. Our series converged by the alternating series test, so we were able to make use of the error term generated by that test, that the error was at least no bigger than the absolute value of the first term not used in the partial sum. Okay, and so if we'd had a different form of series, we might have had to use some other technique to estimate the error, but usually those things can be handled on a case-by-case basis as they come up. So try a couple of these problems. Again, there's a lot involved. Take it slow. Write out all the steps. Don't skip things. And remember, don't be in too big a hurry to multiply things out and simplify, or you lose track of patterns. Thanks for listening. Bye.